Hello, and welcome back to Kerbal Space Program with Ferram Aerospace Research installed. Today we will have a look at the Ferram Aerospace Research user interface. We'll strive to get a high-level overview of the user interface today and omit most details. The user interface consists of 3 dialog windows. One dialog window is accessed from the Space Center and has 3 pages. One dialog window is accessed from the editors and has 4 pages. And the last dialog window is accessed from the flight scene, and it consists of a main dialog grouped into 3 sections, plus access to an extended information data panel and a 4-page subpanel with settings. Let us start with the dialog window from the Space Center scene. We get to it by clicking on the far icon in the toolbar. And it can take a while to pop up, but that's only the first time you use it. It has 3 pages. A lot of these options are a mystery to me. I don't know what they mean, but I will show them anyway. That way, if you know what they mean, you can comment below in the YouTube comment section. Put a timestamp and, for instance, say, I know what the difference is when you select arrow failures create explosions and when you deselect it. That way we'll all get to know. So please do comment if you know stuff from any of these pages. I'll just start out with the difficulty and debug left side. First option, I guess, is if you want to make your vehicles indestructible. The second section is, I believe, the colors used for the graphs in the editor user interface to plot curves of coefficients of lift and drag and so on. This can be used so that it is easier to deploy your spoilers and control your flaps. My setup is that when I press the button to brake, which is bound to the wheel brakes, then if I have spoilers on the plane, they will also deflect. The spoilers are usually my air brakes, so that way the same button activates air brakes and wheel brakes. I have not set up any buttons for flap deflection. I just right-click the flaps in question, and even if you don't set up any keys here, you can still assign hotkeys in the editor when you build the vehicle by way of action groups. The relevant actions are labeled increase flap deflection and decrease flap deflection, and the action to throttle spoilers is labeled activate spoiler. I guess this one is if you want your failed parts to simply detach, or if you want them to fail in a more Kerbal way where they go with a cloud of smoke. Then you can choose to add some extra information to the aerodynamics overlay. Now let me get to the right side here. This is the side where we have difficulty settings. I talked about those last time. I guess there's even an option to type in specific numbers. I don't know what they mean. I don't know what these mean either. But just to reiterate the difficulty settings. This allows you to select the drag model and area ruling, presumably so that we may have even lower drag and build rockets that won't be slowed down much in the atmosphere. That said though, even with full drag, the Kerbal atmosphere is not very draggy and our heavy rockets will easily overcome the drag. The area ruling is the Sonic Mach 1 penalty. If you want to play a career game where the sound barrier is the thing, then you probably want to choose strict area ruling. If on the other hand you think the sound barrier is more of a nuisance to your gameplay, then you might want to choose moderate area ruling or lenient area ruling. Let's go to the second page. This is a lot of boxes that I don't know either. The general idea though is that the different parts and control surfaces can take different amounts of stress before they break. On this page we have some time constants up here. I believe they are so that we can tweak so that, for instance, flaps do not deploy too abruptly. And then the lower half is some atmosphere constants that can be used for the different atmospheres of the celestial bodies. Apparently it has been set up so that Kerbin has some viscosity and 15 degrees Celsius. And Joule apparently has half that viscosity, and Juno seems to have a lot higher viscosity. I'm not sure if the constants make any difference. I haven't used it myself. Please comment if you have experience with tweaking these numbers. That was the first of the 3 dialog windows. Now to get to the next one, I think I will just take the flight scene at the next one, because then we can borrow this glider debris and choose to fly it. To get to the user interface and the flight scene, we again click the far icon in the toolbar. This is then the main window, which has 3 sections. One section with a Mach number, a Reynolds number, and an atmospheric density. One section with a quick line showing cautions about your aerodynamic state. A link to the information page with more data. A link to the 4-page settings subpanel. And finally, some flight assistance toggles. Your flight assistance toggles are a wing leveler, a yaw damper, a maneuvering characteristics augmentation that will maintain a predefined angle of attack by adjusting pitch trim, or at least try to, an angle of attack limiter, and a dynamic pressure control ratio. That is a way to scale the response of these 3 augmentations or assistances so that above a certain dynamic pressure, or for convenience let us just think at a fast speed, we do not want to deflect control surfaces as much as we do at lower airspeeds. So you can toggle DPCR on to lessen the amount of control surface deflection that these 3 assistances command. And for good measure, let us see what we have in the settings subpanel. We have these 4 pages. The first one is what we want to show in the data information panel, which is this one. So currently it is all shown, but I think I will only show dynamic pressure, and then I will show engine parameters. And then you have some information shown that we won't go into, but just for fun, let's see this one, for instance. The fuel fraction means how much of our aircraft mass is actually fuel. Because this is a spent booster, then the fraction made up by fuel is 0. We will get to see the air requirement met value in action in the next video, once we got a jet plane airborne to play with. The next page is tweaks to these. All 5 buttons have a page of their own. The first 3 of these are what is called PID controllers. PID is an abbreviation made up of a P, I, and D, where in turn P is for proportional gain, I for integral gain, D for derivative gain. And then the 4th and even more important component is the mapping to and from the PID controller. In this case, the wing leveler, we get the bank angle as an input, and the PID controller will apply these constants in a way that we will look at later in the next video. And as a result, the PID controller output commands an aileron left or right response. The yaw damper will do almost the same. It would look at your side slip angle and then apply these constants and command a rather left or rather right response. There's one for pitch. There's one for the angle of attack limiter. This one is worth mentioning because I think it does not use these three parameters. Instead, it uses this one as the lower angle of attack limit and this one as the higher angle of attack limit when you enable the option there. And then finally this one just has this particular scaling parameter. It's the threshold at which level of dynamic pressure should the extent of control surface deflection be lessened to account for the greater control surface effectiveness at high speed. I'll just put it back and go to the airspeed indicator settings subpanel. This simply says that in the cockpit and also on the narwhal, the speed will be shown as surface and meters per second because I've chosen surface and meters per second. There are other options available. We'll look at those at another time. Then there's the aero visualization, which is the aerodynamic overlay. You can choose some colors and turn it on and off. And by the way, this is on and off the same way as the button F12. If I press F12, then I have my aerodynamic overlay enabled, and if I click it again, it is disabled. And it is exactly the same as this button. I'll clean up a bit by closing the panels. So that is what the flight scene dialog window looks like. Now let me just recover this vessel and head for the editor to build a jet plane. Let's go into the spaceplane hangar. I'll just go fetch our glider. Just grab it and bring it back to a more usual place. I think I will discard this part at once and empty it of solid fuel. And give it a name. It is the jet plane A. And now let us have a look at the interface. Again, we open the interface by clicking the far icon in the toolbar. It has 4 pages. The first page will show some information about the interaction between the sound barrier and the aircraft. The right-hand side is used to enable some curves, for instance this one, which will show you that the aircraft is pointy at the front, here, and then takes up more and more area as seen from the front, and when we get to the wings it really takes up a lot, and then it takes up less here. And then this one is so that you can diagnose, for instance, here where we go from a very slender profile to a thick profile. The yellow there is very tall. I think this one is kind of an averaged out yellow one, but I'm not sure. Please do tell me if you know what it is though, and I might put it in a future video. Finally, you can debug or visualize the calculation locations, the voxels. This grid of little purple boxes, I don't know if the little purple boxes are visible in the video. Maybe I should just turn these curves off again. The boxes kind of look like purple specks sprinkled onto the aircraft. And in all these pages you have raise gear and height velocity buttons. I will have to double check that the buttons are present on all 4 pages. So the raise gear, lower gear are those ones. The velocity vector is only visible from this next page. This will show you the coefficient of lift and the coefficient of drag, in this case from 0 to 25 degrees angle of attack at Mach 0.2. The graphs look like this. So for instance, the coefficient of lift increases all the way at least up here. The reason that there are two lines is that when the aircraft stalls, it follows this curve, and when you try to unstall it, you have to come all the way back here before the aircraft actually unstalls. And we can see, for instance, the drag and the lift to drag scaled by a factor of 10, that is those 10 there. But what we actually wanted to know is that this white line here is the one called the velocity vector. You see it can be toggled on and off there. This is to show those 0 degrees, that's horizontal, and those 25 degrees, that is when the apparent wind is coming from this angle to the wings. You can set up some parameters here. We can even do an export. We will get to that later, because you don't actually need to do an export. It is automatically exported depending on what branch of FAR you're using. Then we can switch if we instead want to see the effect of Mach number rather than the effect of angle of attack. We can say, I want to know what happens when we accelerate from about Mach 0.5 to a little more than the speed of sound. And we're able to keep, say, 1.5 degrees of angle of attack. We can then look at the graph, which will tell us the drag, for instance. It can be quite difficult to read this graph. That is one of the reasons it might be appropriate to go and look at the exported numbers. We can do that another time. Then there's a third page. The third page is the one that we are most used to. Again, we have these two buttons at the top. We have a way of selecting if we want to have the spoilers deployed or not, and select the flap setting. We cannot control the pitch setting, because the pitch setting is the one that will make the plane fly stably. So in this case, at 120 meters per second at sea level, in this particular configuration, we will need to pull back about 11% on the yoke to deflect the elevators about 11%. And the aircraft would, in those circumstances, fly according to these calculations at a little less than 1 degree angle of attack, and we then have all these numbers. These numbers will tell us stuff like if the equilibrium is disturbed by a little bit, how will the plane react? So if for some reason the equilibrium is disturbed in such a way that we are suddenly going 1 meter per second faster than before, maybe because of a wind shear or something, what would then happen to our speed in the coming moments? It would start to decrease by this number, and conversely, if the speed was disturbed to all of a sudden fly slower than the equilibrium, the aircraft would start to accelerate back towards the equilibrium. Let us just remember this number for a moment. Basically 211% and a negative sign. That 211% and a negative sign is now this one. The page 3 numbers have been copied to this block of numbers. And here we can see what actually happens if all of a sudden the aircraft is flying 1 meter per second faster than the equilibrium. What happens is that the speed, this u, will start at this +1, that's 1 above the equilibrium, and then it will tend back towards equilibrium. That's not all actually, because what happens in the course of 30 seconds? In the course of 30 seconds, the aircraft will at some point be back at its normal speed, but at that point the aircraft will be in a slight climb, which means we will continue to lose speed. Then at some point the aircraft starts to build up speed again. what happens then in 2 minutes? In 2 minutes, the aircraft starts out at +1, then the speed will go down and back up and down and up. But the interesting part, and the fortunate part for us in this case, is that the oscillations become smaller and smaller. The oscillations will die out eventually. That's quite nice. Another thing we can check is what happens if a disturbance takes the form of a 3-degree side slip. The aircraft will experience some oscillations and then return to calm, stable flight. But what if we also had a 3-degree bank angle? We see that the banking turn does not right itself. That behavior is very common for aircrafts. In fact, we see this effect, and we see that effect for a lot of real-world airplanes as well. That is, once the airplane is in a shallow bank, if you really leave the plane to its own devices, it will eventually enter a steep bank, and most planes will, at that point, eventually crash. But of course, this is during 2 minutes, so there is every opportunity that the pilot in the course of these 2 minutes at any point can simply correct this and level the wings. So that are the 4 pages of the editor dialog window. Now I will go and put some jet engines on my jet plane, and we can take the plane flying in the next video. I'll keep the video rolling for another 5 or so minutes while finishing up my jet plane A. I don't need that much fuel. I'll take 15 units each side. That would be plenty for this little Juno. I want an air intake. I'm quite deliberately putting it on the wrong way round, because that way these Junos will run out of air to illustrate a point. This is way too much power. Normally I would set the thrust limiter way lower for an airplane like this one. In this case though, I want to have the ability to use up a lot of air so that we can see what happens when engines are starved of air at a high power setting. Earlier, when I tried to build something similar to this, I kept knocking the tail into the ground when I tried to take off. So I think I need a pair of guide wheels, just like you would on your first bike. Do I have tail ground clearance like this? I'm just going to try like this and see. Out of curiosity, what does the stability page say about speed and angle of attack? Yeah, I think that will take off just nicely at a 50-ish meter per second rotation speed. Let's go get the new aircraft lined up on the runway. I will park the new aircraft on the runway and then leave it there for tomorrow, Kerbal World tomorrow, before recording the next episode. I will go with Bill, because Bill is an engineer, and we want to play around with the PID controller. An engineer seems appropriate for the task, I think. Oop. I forgot about that part. Alright, there we go. Oops. Maybe something like this. And like this. And then we can go and leave the plane here.